Hi guys, welcome to the lesson of partial differential equations. So today we will discuss about the Laplace equation in polar coordinates, and we are going to discuss three particular cases. That is for interior Dirichlet problem for interior of a disk and Dirichlet problem for exterior of a disk, and then we have temperature distribution on an annulus, right? So Laplace equation in polar coordinates is given by this form: r squared urr plus ur plus u double theta is equals to 0, right? And we can also write the equation in this way. So by using the separation of variable, the classical technique we are using since we started the heat equation. So here we will apply the same method, that is separation of variable ur comma theta is equals to r is a function of r, and then capital theta is function of theta, small theta, right? So we know that ur is equals to r prime theta, u double r is equals to r double prime theta, and u double theta is equals to r theta double prime. We will substitute these values in this equation. Say this is equation 1. So we will substitute here and we will get an equation of this type, right? So it's r squared r double prime theta plus r prime theta plus r theta double prime is equals to 0. So on dividing the whole equation by r theta, now we can simplify the equation by dividing by r theta. So we will get an equation of this type that is now easily separable. So we will separate the variables here. We can see that on left side we only have function of r, and the right hand side we have the function of theta. So the variables are separated. Therefore we can equate this equation with lambda, and then we will solve for the three particular cases. That is lambda is equals to 0, lambda 1 is equals to p squared, and lambda is equals to negative p squared. So now we can see here this is equals to 0 and this is equals to 0. So this is an equation of Cauchy-Euler type. So we know that the solution for Cauchy-Euler equation is given by a times m into m minus 1 plus b times m plus c is equals to 0. So this is the auxiliary equation for Cauchy-Euler equation. Since here we can write here a is equals to 1 because the coefficient is 1, and again here again b is equals to 1, so we can write m times m minus 1 plus m is equals to 0, which implies m squared is equals to 0, right? So this implies m is equals to 0. So the equation, the solution is now c1 plus c2 ln r. Right, and for theta we have theta double prime is equals to 0, so it will give the solution in this form c3 plus c4 theta. All right, so from r comma theta is equals to r theta, we can write now the solution in this form, right, for case 1. And for case 2, that is when lambda is equals to p squared, we have the solution in this form. Again, we have a Cauchy-Euler equation here: r squared r double prime over r plus r prime over r is equal to p squared. This r we can move it on right hand side, then we will get this equation. Again, this is a Cauchy-Euler equation with coefficient a is equals to 1. Here is also b is equals to 1, and here c is equals to minus p squared. So we can write the auxiliary equation in this form: m into m minus 1 plus m minus p squared. So from here we can see that m is equals to plus minus p, and for theta we have theta is equals to negative p squared. So we will have these eigenvalues here, and we can generate the solution. Again, the general solution for this case will be ur theta is equals to r times theta. That is, we have the solution for r and theta. We will just multiply the functions, this multiplied by this function, right? So Now we are left with the case 3, that is lambda is less than 0. So lambda is equals to negative p squared. Here is the formulation, and we have the equation again, Cauchy-Euler equation, and another is the simple homogeneous ordinary differential equation. Again, we have the auxiliary equation for Cauchy-Euler equation, and here we have the auxiliary equation for this equation theta. All right, so here we can see that m squared is equals to negative p squared, which means that the roots are plus minus p iota complex roots. Therefore, the solution for the Cauchy-Euler equation is now given by this function a cosine p ln r plus b sine p ln r, right? And for theta, we have c to the power theta plus d to the power negative p theta. Again, we will multiply both solutions and we'll get the general solution for case 3. And this, in this way, we have the solutions, general solution for the Laplace equation in polar form. Now we'll apply these solutions onto the particular prop cases that we talked about earlier. That is for Annulus, this is Annuli, and for interior of a disk and exterior of a disk. So let's start with Annuli. So here we have Annuli, that is if we cut a torus, right? If we cut a torus, so we get this particular Annuli, right? So this type of shape that is that has two boundaries, circular boundaries. One is this circle, and second is this circle, right? So we have two boundaries here, so we will have two boundary conditions. Here you can see ua theta and ub theta, right? And the third condition is we have periodic condition, that is we always know that ur comma theta plus 2 pi is equals to ur comma theta. So in this case, the inner circle is at temperature f theta and the outer is at g theta. So we are going to find the temperature distribution in this particular region, right? So we already have the general solution. Now we just need to apply these boundary conditions and periodic conditions. So let's start applying the periodic condition of on solution 1 that we formulated above, right? So solution was ur comma theta is equals to a1 theta plus b1 times a2 ln r plus b2. So now from the periodic condition, we can apply onto equation 1. So 1 implies that a1 theta plus b1 is equals to a1 theta plus 2 pi plus b1. Because the periodic condition is for theta, therefore we are only using this equation, right? This function. We don't need to use this function, this one. We don't need to use this one here. We are only using this function because the condition is for theta only, right? So we already know from the cases of heat and wave equation that we only use the equation for which the boundary conditions or the conditions are given, right? So here is the ur comma theta is equals to a1 theta plus b1. So periodic condition is applied on this function here. So it's a1 theta plus b1 is equals to a1 times theta plus 2 pi plus b1. So b1 cancel out, which implies that a1 is equals to 0 because this is a1 theta, this is a1 theta plus 2 a1 pi, right? So again, a1 is equals to 0. So the solution is now equals to this one. And we can simplify constants in this manner, right? So it's a naught plus b naught ln r. Now we can move to second equation for equation 4. So using periodic conditions, equation 4 implies this. We will simplify this equation. Here are the steps for the simplification. And now we can see here that this condition will only hold that this whole function is equals to 0 when a1 is equals to b1 is 0. Otherwise, we cannot have a solution that is equals to 0 because e to the power p theta can never be 0, because we already supposed in this case that p is greater than 0. So it's never 0. So it cannot be 0. Here also we said that p is greater than 0 for this case. Therefore, these functions cannot be 0 these ones cannot be zero. Therefore, we are saying that only and only we have the possibility that a1 b1 should be zero to make this condition true, right? So here a1 is equals to b1 is equals to 0, which means that our solution is trivial for this case. So now using the periodic condition on equation 5, so here is the periodic condition again on the equation of theta. A cos p theta, a cosine p theta plus b sine p theta is equals to a cosine p times theta plus 2 pi plus b sine p times theta plus 2 pi. We will simplify and we will then use the angle identities to further simplify these functions, these equations. So finally here you can see that the simplification steps. So this is the most simplified form here, right? So from here sine p pi and sine p pi are we can take it as common. So and 2 is also common, so we'll take it outside. Then we can say that 2 sine p is pi is equals to 0. From here we will get p is equals to n, which is the eigen value for this problem, right? So now we can apply p is equals to n in the equation. Here we will get the solution for this. Now we have here a multiplied by c r to the power n cosine n theta and all this. So for AC, AD, BC and BD we are replacing with these constants, right? A and B and C and D, and to make it simpler. So now we have the principle of superposition. So we have solution from two cases, that is from case 1 and case 3. So we'll add up both the solutions to get the final solution. All right, so this is the final general solution for the equation. Now we'll apply the boundary condition that was given you. A theta is equals to f of theta, which means that now we'll apply r is equals to a. So here is the solution for this, which is equals to f theta, which means that a naught plus b naught. Now we can see that this is a Fourier series, right? General Fourier series. So we have two boundary conditions, ua theta and ub theta, because this is annulus. So and we can see that 1 2 3 4 here. We have we can see here 1 2 3 4 5 and 6 constants. Therefore we need 6 equations, and here we can see that this is a Fourier series. So a naught plus b naught ln a, this is constant, so it will be equals to 1 upon 2 pi times this integral 0 to 2 pi of theta d theta. We multiplied by this 2 here because we know that in Fourier series we have the constant, this constant function, whole constant is called as 1 over 2 a naught. So here is 1 over 2 is missing here, so we multiplied here, right? So that's why here it is 1 over 2 pi times this function 0 to 2 pi of theta d theta. Similarly for a n, a to the power n plus b n to the power negative n, this one, that is the coefficient of cosine. So we know that this will be equals to this function. Then the coefficient of sine is equals to this one. Then again from the second boundary condition we have this equation a naught plus b naught ln b is equals to this function, and then again the coefficients of cosine and sine here, right? So this is the idea of the solution for the annulus. And if we are given with like some conditions like this, that u of a comma theta is equals to 1, let's say, and u of b comma theta is equals to theta, so we can easily solve by only integrating, and then we will solve these equations simultaneously, right? Because we have 6 unknowns and 6 equations, and whereas this b will also be given because this a and b are the radius of the respective circles, right? So the radius will be given, so we can easily calculate the solution, right? So that's all. for now, and then in the next class we are going to discuss Dirichlet problem for interior of a disk and Dirichlet problem for exterior of a disk, and then we will take some more problems. We will see how to solve the problems having the boundary conditions, right? So that's all for the time being. Thanks for watching the lecture. Goodbye.